Credit to Professor Rampton Zan from the University of South Carolina for the slides we'll be discussing. In computing, there are several key metrics that help us understand the performance of a system. Let's dive into three crucial ones. Throughput. This refers to the number of results produced within specific time interval. Mathematically, it can be represented as throughput equals to results by time. It's vital metric for data center managers because it gauges the efficiency and capacity of a computing system. Response time. The metric indicates the time taken from the moment an input is given until the system produces an output. This time includes several components such as time taken by CPU, memory, disk, and network. It can be formulated as response time equals to CPU time plus memory time plus disk time plus network time. It's crucial for individual users as it provides insight to how quickly a system or application can deliver results upon receiving an input. Execution time, also known as CPU time or processor execution time. It provides a measure of actual time the CPU spends processing tasks. The execution time can be derived from the response time minus the idle time, represented as execution time equals to response time minus CPU idle time. The assumption here is that CPU is idle during the non-processor operations. The metric is particularly important to ASIC chip designers or engineers when choosing the right CPU for the computing system. Throughput and time are crucial performance metrics in computing. Let's understand their relationship and significance. Throughput is defined as the number of outputs produced in a given time interval. It's usually measured in operations per second. Mathematically, throughput equals number of outputs produced by time interval. Interestingly, there are scenarios where the throughput of a system can increase while the execution time remains unchanged. You might wonder how this is possible. The answer lies in parallelism. Parallelism refers to a concept of performing multiple operations or tasks simultaneously. Instead of increasing the speed of a single processor, you can improve overall performance by having more processors working at the same time, or by increasing the number of channels a single processor can handle in parallel. Practical example of leveraging parallelism is a bandwidth doubling technique. Take for instance an i7 core processor that use 64-bit data bus. This allows it to transfer twice as much data at once compared to a 32-bit processor, effectively doubling the throughput. The accompanying diagram illustrates a 32-bit processor might handle 4 data units at a time, notably while a 64-bit processor can handle 8. This increase in throughput is achieved without affecting the latency or time it takes to begin the transfer, which remains at 50 nanoseconds in both cases. In conclusion, understanding the relationship between throughput and time and the impact of parallelism can lead to more efficient and optimized computing systems. Performance is a critical metric in computing, helping us understand how a processor or system operates. To enhance the performance of a specific processor, say processor X, our primary objective is to reduce the time it takes for the processor to finish a task. This relationship can be expressed as the following here. The symbol denotes it's proportional to. The equation indicates the performance of a processor is inversely proportional to the execution time. Simply put, the quicker a processor can complete tasks, the better its performance. To compare two processors, for example, processor X and processor Y, we can determine their relative performance. If processor X operates faster than processor Y, their performance ratio can be depicted as this one. Here n represents the factor by which processor X is faster than processor Y. Lastly, it's vital to differentiate between two types of performance measurements. Relative performance measurements. This is a dimensionless ratio comparison. It gives us comparative metrics between two systems without specific units. Absolute performance measurement. Sorry. This is a more concrete metric expressed in units like tasks per second, which is essentially the throughput of the system. In conclusion, understanding and optimizing performance is essential for efficient computing systems, and comparing processor helps in decision making informed decisions. Building on the understanding of performance, let's examine a practical example that focuses on the concept of the relative performance between two processors. Given the first processor, we have two processors. The first one is 64-bit A7, takes 30 milliseconds to execute a video compression program. The second 32-bit A6 processor requires a significant longer 600 milliseconds to complete the same task. Sort. We aim to determine the relative performance of an A7 chip compared to the A6 chip. Solution. To understand which processor is faster and by how much, we can use the formula, this one. Here n signifies the fold increase in the speed. When we plug in our given times, we get 600 millisecond by 30 millisecond, that's equals to 20. This means that A7 processor is 20 times faster than A6 processor for the video compression task. Alternatively, we also state that the execution time of A7 processor is 20-fold smaller than that of A6 processor for the same task. In summary, relative performance provides a comparative metric to determine the speed difference between the two processors, allowing users to make informed choices based on their requirements. Let's talk about processor clock period now. At its core, a processor clock operates by oscillating between high and low signal levels. This is visually represented in the clock signal diagram, where you see several cycles shifting between 0 volt and 1.2 volts. The clock serves as a crucial role in coordinating processor's operations. Specifically, on the rising and the falling edges of the clock signals, two primary events occur. A register in the processor updates its content. A processor commences the execution of an instruction. Now let's discuss the clock period, which refers to clock cycle time, which is essentially the interval of time in between two adjacent rising edges. Simpler terms, it's a duration of one complete clock cycle of this clock signal from one peak to the next. The unit used to measure the clock period can range from seconds to much smaller units like nanoseconds, microseconds, or even picoseconds, given the rapid pace of most modern processors. In most processor designs, the duration of high and low phases are usually equal. This result is what we term as 50% duty cycle, although this remains consistent regardless of a clock period's actual duration. To visualize this concept, consider the oscilloscope operation mentioned. It's a tool that allows us to witness the clock signal's oscillation in real time. We are going to talk about processor frequency. Clock frequency This is a measure of how fast CPU can execute instructions in a given second. Formally, it's defined as the inverse of clock cycle time. In mathematical terms, you can represent it as 1 by clock period. Now, you might wonder, what's a clock cycle? Visualize it as rhythm or heartbeat of a CPU, like we mentioned earlier. The diagram showcases three such cycles with the time duration of one cycle being labeled as one clock period. Clock frequency is measured in units called hertz, which indicates the number of cycles occurring in 1 second. This is sometimes referred to as clock rate. To give a clearer picture, let's look at some examples. The clock cycle period of 10 nanoseconds corresponds to a clock rate of 100 millihertz. Similarly, 5 nanoseconds equals to 200 mHz. 2 nanoseconds result in looping 500 mHz clock rate. It's essential to note that when designing processors, engineers commonly work in the units of nanoseconds for time and gigahertz for frequency. This is because modern processors operate incredibly fast with billions of cycles in just a second. In conclusion, processor frequency is a critical metric in understanding CPU speed and performance. A higher frequency often indicates higher processor, but other factors like architecture and efficiency also play a crucial role. Now let's delve into the performance implication of clock rate in computer processors. To begin with, there are three common strategies to enhance the performance of a processor. First one, increasing F clock frequency. By doing so, each instruction in the processor is executed more rapidly, resulting in a faster performance. Number two, reducing the number of clock cycles. This is achieved by either designing a better instruction set or by optimizing the compiler or use fewer yet more powerful instructions. It's important to note that all instructions need at least one clock cycle, but many instructions might require multiple clock cycles to be completed. Utilizing parallelism. This involves running multiple instructions simultaneously. However, this slide focuses on single processor and the depth of parallelism will be explored later in the course. Now, if we consider the first two factors mentioned above, we can determine the CPU execution time. It's the product of number of clock cycles required to complete a program and duration of each clock cycle. Mathematically, this can be represented as CPU execution time, number of clock cycles to complete the program multiplied by how long a clock cycle is. To simplify it further, CPU execution time equals number of clocks into period. In essence, to optimize the performance of a CPU, we either reduce the number of clock cycles or decrease the period of the cycle. Both these strategies ultimately lead to reduction in overall execution time of the CPU. To sum up, understanding the clock rate and its impact is vital for anyone looking to grasp the intricacies of CPU performance. In this example, we are presented with a real world scenario that illustrates the importance of clock frequency in computing tasks. Let's break it down step by step. Given Facebook is using a bulk AES encryption task which takes 10 seconds on an AMD FX1 processor operating at a clock frequency of 2 GHz. Now a new AMD FX2 processor has arrived. Let's suppose clock frequencies between 500 MHz to 4.3 GHz. However, instruction on FX2 takes 20% more clock cycles to execute than on the FX1. Objective: We want to find out value for the clock multiplier register, ensuring that new FX2 processor completes the same encryption task in just 6 seconds. Solution. Firstly, we calculate the number of how many clock cycles the FX1 processor uses for the task. Using the formula, we get the result 20 into 10 to the power of 9 clock cycles. Second one, FX2 requires 20% more clocks. There is 1.2 into 10 to the power of 20 E9 clocks, that is 24 E9 clocks for the same task. Now, the clock rate. 4 into 10 to the power of 9 clock cycles equals to 4 gigahertz. So the clock for F2x, thus to meet our objective, the F2x needs to operate a clock 4 gigahertz within its specified range by setting the processor to this rate. The encryption task would complete in desired 6 seconds on the F2x FX2. Now we're going to talk about a concept called CPI, or clocks per instruction. This is a vital metric in computer architecture, giving us insight into processor's efficiency. It's essential to know that different types of instructions have varied amounts of clock cycle to execute. For instance, multiplication consumes more cycles than addition. Floating point operations generally take more cycles compared to integer operations. Accessing memory is more time consuming than accessing register. The core idea of CPI is to give an average. It represents the average number of clock cycles taken for each instruction in a given workload. Let's take a look at the practical example provided in the slide. Here the workload consists of 7 instructions: add, multiply, shift, read. Among them, these instructions in total take 14 clock cycles to execute, and the CPI is calculated, that is 2.0. It is crucial to note that CPI can vary across processors such as Intel Core i5, AMD FX, and others. Each processor based on its architecture will have its unique CPI for a specific set of instructions. When evaluating the CPI of a processor for a particular workload, the number of general small real number like 2.3 or 3.1, especially for a non-pipeline single core. Interestingly, the CPI can sometimes be less than 1, especially when parallelism is used. The units of for CPI are clock cycles per instruction. An alternative metric often used is IPC, or instructions per clock, which is simply the reciprocal of CPI. To summarize, CPI provides a clear picture of efficiency of a processor in executing a set of instructions. The lower the CPI, the fewer clock cycles are required per instruction, indicating a more efficient processing. We'll focus now on understanding the number of clock cycles required to execute a program. At the heart of any computer and efficiency, the speed of program execution are paramount, and metric offers invaluable insights. To determine the number of clock cycles required to execute a program while utilizing the following relationship. This one, where clock represents the total number of clock cycles. Instruction count refers to the total number of instructions given in a program, and CPI is the average number of clock cycles for each instruction, as we previously discussed. Once we computed the total clock cycles, we can delve into ascertain the CPU execution time for the program. The formula is CPU time, instruction clocks, and cycle time. Where cycle time is the time taken for one clock cycle. Building upon this, we can further refine our understanding by incorporating the previous equation. which leads us to CPU performance equation. CPU time equals to instruction count into CPI into cycle time. The equation elegantly encapsulates three core components: total instructions of a program, efficiency of a processor in terms of clock cycle per instruction, inherent speed of the processor signified by the cycle time. So, to sum up, by leveraging these formulas, we can get a comprehensive understanding of the time and the efficiency aspects related to the program execution of us on a CPU. In this example, we'll be delving into comparison of both processors, MIPS 34K and MIPS 74K, both of which utilize the same instruction set. Given MIPS 34K processor has a clock cycle time of 250 picosecond and an effective CPI of 2 when running a quicksort program. The MIPS 74K on other hand operates with clock cycle time of 500 picosecond but boasts a more efficient CPI of 1.2. Both these processors generate identical machine code when using specific compilers. Sort. Our primary objective here is to discern which processor performs faster by what magnitude. Solution. Using the CPU performance equation, execution time equals to instruction count times CPI times cycle time. Given that both processors execute identical machine code, their instruction count remains the same. Let's denote this as instruction count. For MIPS 34K, execution time equals to instruction count times 2 times 250 picosecond equals to 500 times instruction count per picosecond. For MIPS 74K, execution time equals to instruction count times 1.2 times 500 equals to 600 into instruction count per picosecond. Clearly, the MIPS 34K showcases a faster performance since its execution time is lesser. To gauge the relative performance, one can use the inverse ratio of execution time. Execution time of MIPS 74K equals to execution time of MIPS 34K equals to 600 into 500 divided by 500 equals to 1.2. This infers that MIPS 34K processor is 20% speedier than MIPS 74K, even for a quicksort word lot where the latter operates at a clock cycle that's twice as fast. In conclusion, while clock speed is vital, other factors such as CPI play a significant role in determining processors' overall performance. Now we'll talk about effective CPI. Effective CPI for a workload. So, firstly, what is effective CPI? Effective CPI stands for clocks per instruction, and effective CPI gives us an average figure considering various types of instruction a processor can execute. It is computed as weighted average taking into account both the number of clocks each instruction type requires and the proportion of those instruction types within a given workload. To break it down, n represents the number of different instructions classes in the workload. Proportion I denotes share of the total instruction count contributed by each instruction class. CPI I is the number of clock cycles needed for the instruction for that particular class. Now to put this concept into real world scenario, consider an ARM Cortex processor working on an AES encryption workload. We have three instruction classes: integer, floating point, data, and data transfer. Each class requires a specific number of clock cycles per instruction and contributes differently to the overall workload as shown in the table. Our objective is to compute the effective CPI and effective IPC for this ARM Cortex CPU when performing AES encryption. Using the provided data, we find the effective CPI 6.4. This means on an average, each instruction executed spends 6.4 clock periods. Furthermore, effective IPC is 0.156, telling us the number of instructions executed per clock cycle. In essence, effective CPI helps us gauge the efficiency of our processor concerning various instruction types, enabling more informed decision when optimizing or comparing processors. In this example, we'll explore the concept of CPI or clocks per instruction and determine the execution time for a program. Given we have a program consisting of 40% arithmetic instructions, each requiring 5 clock cycles, 30% branch instructions taking 2 clock cycles, 30% data transfer instructions needing 12 clock cycles. The program contains a total of 30,000 instructions and is executed on a CPU with 3 GHz clock. Our objective is to find out the execution time of the program. Solution: general formula to determine the CPU performance is execution time equals to instruction count into CPI into cycle time. First, let's compute the CPI using the given proportions and the clock cycles. CPI equals to 0.4 times 5 plus 0.3 times 2 plus 0.3 times 12 equals 2 plus 0.6 plus 3.6 equals to, this is CPI of 6.2. Given that our CPU's clock rate is 3, the clock period or the cycle time is inverse, which is approximately 1 by 3 times 10 to the power of minus 9 seconds or 0.33 nanoseconds. Given the formula, execution time equals to 30,000 instructions times 6.2 times 0.33 nanoseconds. The result in an execution time is 62 microseconds for the program. In conclusion, understanding CPI allows us to make informed predictions about a program's execution time on a specific hardware. Let's delve into more common conceptions regarding CPU performance. The topic at hand is, does a higher clock frequency necessarily mean a faster processing speed? Firstly, it's crucial to understand the CPU clock frequency, often referred to as clock rate, is not an exhaustive indicator of CPU's performance. While a higher clock rate might imply faster processing speeds, various other factors come into play, such as the efficiency of the CPU architecture. For instance, let's consider an example: a Wi Fi convolution task that executes 1000 instructions on both Intel and AMD devices. The Intel Core i3 CPU has a clock rate of 1 GHz and an effective clock per instruction of 4. On another hand, AMD FX CPU boasts a faster clock rate of 2 GHz but has a higher CPI of 10. Our objective is to determine the processor between the Intel i3 and AMD FX offer superior performance for the Wi-Fi convolution task. Solution: execution time equals to instruction time into CPI into cycle time. The execution time for Intel Core i3 is calculated as 1000 times 4 times 1 times 10 to the power of minus 9, which is equal to 4 microseconds. For AMD FX, execution time is 1000 times 10 times 0.5 times 10 to the power of minus 9, amounting to 5 microseconds. What's the key takeaway? Despite AMD FX having a superior clock rate, its execution time is lengthier. Hence, for this specific task, Intel Core i3 offers better performance even with slower clock rate. In conclusion, while clock frequency is an essential aspect of CPU performance, it's not the sole determinant of the CPU performance. Always consider multiple metrics including CPI and architecture efficiency to get a holistic view of the processor's performance. Then let's talk about the difference between dynamic and static instruction count. To illustrate this, let's take a look at the basic assembly language program fragment. The program does the following: sets the loop index to 0, reads data from memory index 50, reads data from memory address 51, adds data to produce a result, increases the loop index by 1. If the loop index is less than 5000, it goes back to step 4. Once the loop is finished, the result is written to memory address 52. Now let's take a look at two types of instruction counts. Static instruction count. This is the total number of instructions in our program as written by a human program. Here we have 7 instructions. It gives us an idea about the size and the code in the memory of the disk. Dynamic instruction count. This represents the actual number of instructions executed by the CPU when the program runs. Given the loop structure of the program, the instructions within the loop will be executed multiple times. In this case, the dynamic count is calculated as 3 for the initial 3 instructions plus 3 for the looped instructions executed 5000 times plus 1 for the final write instruction. A total of 15,004 instructions executed by the CPU. It's essential to understand that when calculating in execution time, we always use the dynamic instruction count. This is because it reflects the actual workload experienced by the CPU, taking into account loops and conditional branches. In summary, while static instruction count provides insight into the code size, Dynamic instruction count offers a more accurate representation of the CPU's workload during the program execution. Many of you might be familiar with the term MIPS while referring to a specific band of processor. However, apart from that, there is also MIPS metric, from which the brand originally derives its name. The term MIPS rate stands for million instructions per second. It's synonymous with another term MOPS, which means millions of operations per second. Both are metrics used to quantify the performance of a CPU. So, what does MIPS rate measure? It gauges how many instructions a CPU can execute in 1 second. This is a crucial metric as it gives us a glimpse into raw computational performance of a processor. To determine the MIPS rate, you can use the formula MIPS equals the instruction count by execution count times 10 to the power of 6. And another way to represent this is MIPS equals to instruction count by instruction count times CPI by clock rate into 10 to the power of 6 equals to clock rate by CPU into 10 to the power of 6, where CPI stands for cycles per instruction and it represents the average number of clock cycles an instruction needs to be executed. In essence, the MIPS rate provides a standardized measure to compare the processor of different processors using, helping users and engineers choose the right CPU based on their computational needs. Today our focus is on MIPS per milliwatt and its significance in evaluating the energy efficiency of the computational devices. Efficiency here relates not just to computational power but also energy consumption. To start, let's talk about energy consumption. Energy measured in joules is given by the product of power in watts and execution time. The formula energy joule equals to power watt times execution time. Moving on, we have the term MIPS per milliwatt. This represents how many million seconds a processor can execute every milliwatt of power it consumes. It's a metric that helps us gauge energy efficiency of a CPU. The formula for this is MIPS milliwatt equals to instruction count by execution time to the power of 10 to the power of 6 divided by MIPS power energy by execution time to 10 to the power of 3. Lastly, there is TOPS, which stands for trillions of operations per second per watt. The metric is similar to MIPS per milliwatt but on a much larger scale, typically used in high performance computing systems. The formula is TOPS by watt equals to instruction count by execution time into power into 10 to the power of 12 equals to instruction count by energy into 10 to the power of 12. In summary, while raw performance like MIPS is important, when we are considering mobile devices, IoT devices, and other battery power devices, the MIPS slash MW and TOPS slash W becomes crucial metrics. This helps strike a balance between performance and energy consumption, ensuring that our devices are both powerful and sustainable. Let's talk about benchmarking, a critical tool in assessing the performance of a computer system. To start, what's a benchmark? Simply put, benchmark consists of a set of programs executed to gauge the performance of a computer system. These benchmarks give us measurable metrics to compare different systems or components against each other. Imagine a scenario where we have to call models or brands of processor, let's call them X and Y. If we are tasked with determining which of these is faster for a specific type of application or a task, how would we go about it? A solution is benchmarking. By executing the same benchmark program on both an X and Y, then comparing their execution times, we can determine which processor performs better for the specific task. However, it's essential that benchmark reflects real world usage. This means a good benchmark should comprise a realistic mix of instructions. Some categories of these instructions include arithmetic or scientific computation, graphic related tasks, or text processing. These categories ensure that benchmark tests various capabilities of the system, giving a comprehensive view of its performance. For those interested in diving deeper into benchmark result and comparison, there is a website that lists CPU performance for different benchmarks. You can visit the following website to explore a lot of data points and comparisons. In conclusion, benchmarking offers a systematic approach to compare the performance of different computer systems or components, ensuring that we make informed decisions when choosing the or recommending hardware. SPEC stands for System Performance Evaluation Corporation. It's an esteemed organization in computer industry, and here's what you need to know about it. SPEC is essentially a consortium of companies that come together to develop benchmarks. Now, why would multiple companies want to do this? The reason is simple. Having a diverse set of companies produce benchmarks help in reducing biases. If only one company were to produce benchmark, there could be concerns about favoritism or skewed results. Multiple perspectives ensures a more balanced and a comprehensive benchmark. But there's something else we must remember when discussing benchmarks. Often one program's measurement might not give us the full picture of a CPU's performance. Think of it this way: if you were to judge a car's performance solely by its speed, and you'd miss out on understanding its fuel efficiency, durability, safety features, and so on. Similarly, SPEC realizes that one benchmark might not capture all the nuances of the CPU's capabilities. Hence, SPEC releases suites of benchmark. When within a suite there are multiple programs, each designed to test a particular aspect of the system. For instance, one program might be focused on CPU operations while other might target memory accesses. And for those of you who are interested in diving deeper, SPEC provides ample resources. You can visit their official website, which is displayed on the slide, for a treasure trove of information. Additionally, there is specific documentation available on 2006 CPU benchmark, which could provide insights into how benchmarking methodologies have evolved over years. In summary, SPEC Benchmarks offers a holistic, unbiased approach to assessing system performance. Thanks to the collaboration of multiple companies, the comprehensive nature of their test suits. On this slide, we have a comprehensive overview of SPEC benchmark set. These benchmarks are essentially programs or algorithms designed to test and measure the performance of computer systems. The idea is to simulate the real world applications and scenarios that a computer push the computer's limits in a specific area. Let's break down on what's on display. On the left side, we see 12 integer benchmarks, primarily written in C and C++. Here are some notable ones. gzip tests compression capabilities. VPR deals with FPGA placement and routing. GCC evaluates the performance using the GNU-C compiler. Crafty, a chess program examining logic processing and decision making. Parser, a word processor program that stresses text manipulation capabilities. Yarn, centered around computer visualization, and so on. Each of these benchmarks tests a unique aspect of computational performance, particularly integer operations. Now shifting to the right side, we have 14 FP benchmarks that are written in Fortran 77, 90 and C. These are floating point benchmarks focused on heavy mathematical computations. Wise pertains to quantum chromodynamics, a branch of theoretical physics. Swim simulates shallow water model. Grid, a multi-grid solver in 3D potential field testing spatial calculations. Mesa dives into 3D graphic libraries and their performance. Art concentrates on neural networks and image recognition, and many more. These benchmarks evaluate systems' ability to handle intricate mathematical operations, especially involving floating point arithmetic. In essence, these spec benchmarks cover a wide range of computational tasks from simple compression to high-end physics simulations. By running these on a system, we get a comprehensive understanding of its strength and potential bottlenecks. Now, spec ratio. This is a fundamental metric used in benchmarking to evaluate the performance of a computer system. Imagine running an entire suite of benchmark programs on a computer. For each of those programs, we calculate a specific ratio based on the execution time of the program on a computer being tested compared to a standard or a reference computer. The formula provided showcases this. SPEC ratio A, execution time on reference by execution time on a computer A. The resulting value, termed as spec ratio for the program, gives us a comparative measure of computer's A performance against the reference. A spec ratio greater than 1 indicates that computer A is faster than the reference, while spec ratio lesser than 1 means it's slower. Now, what happens when we want to compare two different computers using these spec ratios? This comparison is independent of the reference computer. The slide depicts a formula that enables this comparison. Spec ratio A by spec ratio B equals execution time reference by execution time A by execution time reference by execution time B, which is equal to execution time B by execution time A. Finally, performance A by performance B. From the formula, we can see that computer's execution time cancels out, thus giving us a direct relationship between the performance of a computer A and B. In a nutshell, the spec ratio provides a standardized way of comparing the performance of different computer systems against common reference, making it an invaluable tool in the field of computer benchmarking. Geometric benchmarking score. When benchmarking system is not just about individual performance metric but also deriving an overall score to represent system performance. This is where spec score comes into play. Instead of taking simple average of the spec ratio, the spec scores uses a geometric mean. Why the geometric mean? It ensures that all benchmarks have an equal weight even if their individual scores vary widely. To calculate the geometric mean, you multiply the spec ratios together, take the nth root where n represents number of spec ratios. The formula is displayed as the following. Therefore, we talk about spec ratio, it's simply the geometric mean of all the spec ratios obtained during the benchmarking. The final formula is shown as following. In essence, the spec score gives us a consolidated metric to evaluate a system's performance by considering all the individual's benchmark results. We are benchmarking two computer systems labeled A and B against the reference computer R. We have data for three workloads: performance of a spec suit, CPU, memory, and graphics. For each program, execution time of the reference system R, system A, and system B are provided. Our goal is to determine the performance ratio for spec scores for both systems A and B, and ultimately derive the spec score for the to compare the performance. How is it done? First, calculate the spec ratio for each workload by taking the ratio of execution time on the reference computer to the time on the computer A or B. For system A, CPU equals to 5, memory 6, graphics 6. For system B, 20 by 5 4, memory 30 by 6 5, graphics 12 by 4 3. Next, we compute the spec score for both the systems using geometric mean formula as follows. We get 1.26. This means system A is roughly 5 times faster than the reference system for the given workloads. Furthermore, when compared to system B, system A is 1.26 times faster for these three benchmark programs.